So, very good morning everyone. Welcome to the YouTube platform of IMS GATE Academy. And I welcome you to the foundation series conducted by IMS GATE Academy for the subject of strength of material. In the previous session, we have already seen how the loads are applied over any structure, then what are the effect of these load and how we consider the effect of these load. The effect of these load is the production of internal resisting force inside a member, and this internal resisting force per unit area is termed as the stress that is developed. A student should not confuse between stress and pressure. Stress is internal resisting force per unit area, whereas pressure is the external load per unit area, right? Similarly, we have discussed about shear stress. So, shear stress is basically the shear force which will act along the surface per unit resisting area. So, that is how we calculate the shear force, right? Then we have seen the relation between all the elastic constants, that is Young's modulus, shear modulus, bulk modulus and Poisson's ratio. One more thing I would like to add here, Poisson's ratio gives us the relation between lateral strain and the longitudinal strain. If I have this member and I'll pull this member with a tensile force, the length of the member will going to increase, but the other two dimension will going to contract for a member, right? So, the relation between lateral strain to the longitudinal strain is explained by the Poisson's ratio. So, Poisson's ratio is minus lateral strain divided by longitudinal strain. Then we have seen four relation for elastic constants. The first one is E is equals to 3K1 minus 2 mu. From there, we come to know that for incompressible material or for rigid material, the value of Poisson's ratio is 0.5, right? So, we have a detailed discussion about all the elastic constants that are used in order to calculate the property of a material. Today's lecture is dedicated to, once you apply the load over any member, how this member will going to deform. As the name says, topic name is elongation of the bars. So, elongation of the bar or the deformation of the bar will only happen when you apply the tensile or compressive load over the member. Okay. So, let's begin this. Topic is elongation of the bar. So, first of all, let me consider one bar over which I'll apply some tensile force. This is my bar. Just check and confirm me once. Okay, so this is my bar and over this I'll apply the tensile force like this. So, this P is my tensile force that I'll apply over the bar, and it is very much clear that if I apply the tensile force over this bar will undergo deformation or elongation. How much elongation this bar is undergoing, that we need to calculate, right? So, we need to calculate the amount of elongation this bar will undergo. So, this is the total amount of elongation this bar is undergoing. Initially, the length was L, now the length is L dash. So, the change in length is delta L. Change in length is equal to delta L, and this we need to calculate, that corresponding to this load how much this bar is getting deformed, right? So, in order to calculate that, we have one relation, stress is equals to E into strain. This we already know. Stress is P by A, where A is the cross sectional area and P is the external load which is equal to the internal resisting force, right? Then you have E into delta L by L. Just rearrange this entire thing and you will come to the conclusion that delta L is equals to PL by AE. So, this is your deformation that will going to happen if you apply the load. It doesn't matter whether you are applying the tensile load or you are applying the compressive load. If you are applying the tensile load, you will observe the increase in length, whereas if you apply the compressive load, you will see decrease in length. But the amount of length that will going to change is PL by AE. right? And this change in length is corresponding to the external load. So I think this is very much clear to you, right? Let's solve one gate question which came this year. The question is something like this. So you have two members. First one is this member, second one is this member, right? And these members are hanging through a support. These members are hanging through a support, right? So this is my support through which these members are hanging. So this is my support through which these members are hanging. This is point A, this is B, this is C. You have one 50 kilonewton load acting at the bottom of the member. You have 100 kilonewton load acting on the either side of the member. You have 100 kilonewton load acting over either side of the member. This year in GATE examination, that is for GATE 23, this was the question. What is given in the question? I'll write this. So this is GATE 23 and also for GATE 2003. This question came twice and it's a simple question. First of all, ignore the self weight of the member. Ignore the self weight right? Ignore the self weight of the member. Second thing, good morning Thiru sir, good morning Pragya sir. So you have to ignore the self weight of the member and you need to find where the maximum tensile stress will come. And what is its value? This question was asked twice in GATE examination, right? And why it seems to be an important question, we will going to discuss this. But observe this question first, analyze it, and then understand how to solve this question, right? So you have two members given to you, member AB and member BC. Both of these members are connected and they are hanging from a support. A load of 50 kilonewton is acting over this member BC and two loads of 100 kilonewton and 100 kilonewton are acting on member AB. The cross-sectional area for both these members is, both of them are square sections. Both of them are square sections. Both of them are square sections. For AB, cross-sectional area is 100 cross 100 mm. And for BC, area is 50 cross 50 mm. Right? So you have all these data given to you. Just try this question. This is an easy question. First thing that I would like to tell you, this member is a prismatic member. Both of them are prismatic member. And what are prismatic member? The members for which cross-sectional area is constant throughout the entire depth. Those members are termed as prismatic member, right? For prismatic member, if load is constant, then over their entire length, the stress value will also be constant. Area is constant, load is constant. So obviously, stress for the entire length will also be constant, right? So let me consider this member BC. For BC, let me calculate the stress. for member BC, let me calculate the stress. So stress for member BC is equals to load P1 divided by area of BC. For BC, only one load is acting, that is 50 kilonewton, right? So P1 is 50 kilonewton. So 50 into 10 raised to power 3, and this will be in Newton, divided by area of BC, which is nothing but 50 into 50, and this is in mm square. So if you calculate this, you will find that 50 and 50 will going to cancel out, and this is 1000 by 50, which comes out to be 20 Newton per mm square. So sigma BC comes out to be 20 Newton per mm square, right? And I have already told you this, Newton per mm square is equals to megapascal. So either you write 20 Newton per mm square or 20 megapascal, one of the same thing. Why I am writing both the units? Because the student seems to have certain kind of confusion when it comes to the unit. So this clarity also you should have, right? Now consider the another portion, that is for AB. Consider AB. For AB, the total amount of load that are acting is 100 kilonewton, 100 kilonewton, and one more 50 kilonewton. We will not consider the weight of BC because in the question it is clearly mentioned that you have to ignore the self weight of the member. Okay. So for the member AB, the total amount of load acting are, for AB, stress in AB is equals to load P2 divided by area of AB. Load in AB is equals to 100 kilonewton plus 100 kilonewton plus 50 kilonewton, and it is kilonewton, therefore 10 raised to power 3, now it comes into Newton, divided by area of member, that is 100 cross 100, and this is in mm square, right? So this comes out to be 250 kilonewton, 250 kilonewton into 1000, okay, divided by 10,000. So when you do the calculation, you will come to the answer of sigma AB is equals to 25 Newton per mm square or 25 megapascal or 25 megapascal. So this is the stress value for the member AB. Now just compare both of these members. So you will clearly find for member AB, the maximum value of stress will going to happen. So this is just one part of the question that was asked in the examination. What if I give you the length of these members? Okay. So for this question, for member AB, you will going to have the maximum value of stress. What if I say this member is having of length 3 meter and this member has a length of 2 meter, and the value of Young's modulus is, 2 into 10 raised to power 5 megapascal, right? What I said, the length of this member is 3 meter, the length of this member is 2 meter, the value of Young's modulus for both of these material is 2 into 10 raised to power 5 megapascal. Now you need to calculate the total amount of elongation this point C will undergo, right? What do you need to calculate? You need to calculate total amount of elongation this point C will undergo. When all these load conditions are applied, how much deformation this point C will undergo, by how much amount this point C will going to deform, right? So again, this question becomes a little tricky. I will not say difficult, but just a little tricky, right? I have just slightly twisted the question. So if you again observe these two members, both of these members are hanging. First observe this member BC. Due to this 50 kilonewton load, this BC will undergo some amount of deformation delta 1. this BC will undergo some amount of deformation delta 1, right. So, this is the deformation due to member BC. But also you have this member AB, and this member AB will also undergo some deformation due to these loads, and that deformation will equal to delta 2. Deformation of the member AB is equal to delta 2. So, the total amount of deformation this point C will undergo is equal to delta 1 plus delta 2, is equal to delta 1 plus delta 2, right. Delta 1 is the deformation of this member BC. Delta 2 is the deformation of this member AB due to these external loads, right. So, this is how you need to calculate the total deformation this point C will undergo. So, let us calculate that. First we calculate delta 1. So, deformation calculation. For BC, delta 1 is equals to P1 L1 upon A1E. This is the total deformation that BC member will undergo. P1 is 50 kilonewton. So, this is 50 into 10 raised to power 3. Length is 2 meter. So, 2000 meter converted into mm, divided by area, which is 50 cross 50 mm square, and this E is 2 into 10 raised to power 5. Again this is megapascal, which is nothing but Newton per mm square. So, you have 1 mm in the top, then you have 2 mm idhar, you have 2 mm, that is mm square, you have at the bottom. So, this mm square and this mm square will going to cancel out. This Newton and this Newton which is present in the numerator will going to cancel out, and you will going to have the deformation in mm, right. Student have these confusions, these slight confusion will going to vanish your complicated calculations like anything. So, whenever you are calculating, just calculate it like a school going boy, right. You have to write all the units, then cancel out everything, so that there is no scope of confusion, because if mm is converted into meters or some centimeters, your answer will be totally incorrect. So, this is how you proceed, right. So, just do the calculation for this. So, this is like this 10 raised to power 3 and 10 raised to power 5. So, here you have 2 zeros. These 2 zeros will be cancelled by these 2 zeros. So, you have 20 into 50. So, 50 and 50 cancels out. So, 20 divided by 100. So, 20. So, this is like 0.2 mm. So, this is the deformation for this member BC. This is the deformation for the member BC. Now, calculating it for AB. For AB, your delta 2 is P2 L2 divided by A2 into E. This is the net change in length for the member AB, right. Now, just substitute the value. This P2 is 250 kilonewton. So, this is 250 into 10 raised to power 3 into length of the member is 3 meter. So, this is 3000 divided by A2, which is 100 cross 100 mm square, and E2 is 2 into 10 raised power 5. Now also this delta will come in mm. Just do this quick calculation. So you have 250 into 1000 into 3000 divided by 10,000 into 2 in. So this comes out to be 0.375. So this is the second deformation that you got, right? This is your second deformation. This is delta 1 and this is delta 2. The total change in length or the total amount by which this point C will come down is delta 1 plus delta 2. So the total deformation of C is delta 1 plus delta 2. So this is like 0.2 plus 0.375. So this comes out to be, so total deformation of C comes out to be 0.575 mm. Okay, so this is the net change in length or the net amount by which the point C will come down. Okay, this is again, if you come back to the question, if you again come back to this question and observe this question carefully, so C will come down by the amount of delta 1 plus delta 2. Now if the question says by how much amount this point B will come down, so you will say this point B will come down by the amount of this delta 2. That is the net change in length for this member AB, right? So this member AB will undergo the deformation of delta 2 and point B will only come down by the amount of delta 2. This B will come down by the amount of delta 2. This change is delta 2. So B will come down by the amount of delta 2. So the deformation of point B is delta 2. So total deformation of B is only equal to delta 2, which is nothing but 0.375 mm. Similarly, if you observe point A, so this is A2E. If you observe point A, so point A is attached to the support. So point A will do not undergo any deformation, right? So if you need to calculate the deformation of different points, that is how you need to calculate, right? So for point C, it will undergo by the total deformation of delta 1 plus delta 2. B will only undergo the deformation of delta 2 and A will be at zero deformation. It will not going to deform, right? So this is one of the question that was asked in GATE examination for twice with same data. There is not even the change in data when it was asked in 2003 and 2023, right? This year also this same question was there in the examination, right? So this is an easy one. Okay, moving to the next section. The next topic of discussion is bars connected in series. Next topic of discussion is bars connected in series. Right, for suppose these are the 3 bars, the length of the bar is L1, L2, L3. Area of cross section is A1, A2 and A3. Young's modulus for the material is E1, E2 and E3. So these are the detail given to us, and these bars are connected in series, that is one after the other. The load is applied like this. This is the amount of load P that is applied over all the bars, right? And this load is passing through the longitudinal axis of the member, okay? Now, how we say that these bars are connected in series? So, first thing is, when the amount of load acting over individual members is same, right? And they are connected along their longitudinal axis, then these bars are said to be connected in series. So if you just consider individual member and observe the amount of forces that are acting. So if I draw this first member, so this is my first member, this is my second member, and this will be my third member. Right, so these are the 3 members. I'll name them also. So this is member AB, then BC and then CD. So this is member AB, then BC, then CD. Right. Consider this member. For this member, the total amount of load that is acting is P. The total amount of load that is acting is P. Similarly, when you consider this member, for this member also the total amount of load that will be acting will also be equal to P. Right, now you will be confused, sir, how you are saying this directly, right? Observe this junction B, right? So this is my junction B. These two are connected to each other. For this junction B, this member will be resisted by this member, and this member BC will going to pull this member by the amount of P. But this member AB will going to oppose this pull and will going to apply the same pull of P over this member BC, right? So this is how this junction BC will behave. And due to the internal reaction forces that are developed at this junction, you will see these forces over this section of B, right? Same thing will happen at the section of C, and you will going to see a same pull of P and a same pull of P for this member CD, right? So this is the load condition, and these are the free body diagrams. These 3 are the free body diagrams. So these 3 are FBD, that is the free body diagram for all the member AB, BC and CD. So the first thing is clear, if the members are connected in series, right, the amount of load acting all these members will be same. So for the members connected in series, the amount of load that will be acting over these members will be same. So for the members in series, for bars connected in series, load acting over all the members is same. Load acting over all the members is same. Right. So the first observation is load acting over all the members is same. Okay. Now observe these members again. These members have different lengths, different area of cross section and different Young's modulus. All these three members have have different values of length, area and Young's modulus, right? So when we calculate the amount of deformation this member AB will undergo, will come out to be delta AB. Similarly, we can also calculate the amount of deformation this member BC will go. So this comes out to be delta BC and this will be delta CD. So the total amount of deformation this entire assembly will undergo will be delta AB plus delta BC plus delta CD. So the total amount of deformation, total deformation is total deformation is the algebraic sum of individual deformation. Total deformation is the algebraic sum of the individual deformation. And what I am saying is, first thing, load in member AB, PAB, is equal to load in member BC is equal to load in member CD, and this is equal to P. Second, total deformation delta is the sum of individual deformation, delta AB plus delta BC plus delta CD. So this is how you calculate the total deformation for these bars, right? So if I have to write delta AB, how I will write delta AB? So delta AB is nothing but PL1 upon A1 into E1. Since load is same for all the members, so I will write P L1 upon A1 into E1. Similarly, for delta BC, it is P L2 divided by A2 into E2. This is your delta BC. Delta BC is the second member, so the length is L2, area is A2 and Young's modulus is E2. Similarly, your delta CD is equals to P L3 upon A3 into E3. So this is how you calculate the total deformation for member AB, for member BC and for member CD. In order to calculate the total deformation, just add all the deformation, right? So if n number of members are connected in series, so first thing is load acting in all the members is equal. Second thing is total deformation is the sum of individual deformation that is occurring. Just try this question. This kind of member you have and a load acting is 100 kilonewton. load acting is 100 kilonewton. This is 100 kilonewton. For this, area is 50 mm square. For this, area is 100 mm square. This is 20 mm square. And this is 120 mm square. These are the areas. Young's modulus for this is 1 into 10 raised to power 5 megapascal. This is E. For this member, it is 2 into 10 raised to power 5. For this member, it is 3 into 10 raised to power 5. And for this member, it is 0.5 into 10 raised to power 5 megapascal, right? Load is, this one is also 100 kilonewton. So I want the total amount of elongation this member will undergo. Just try this question. Just try this question, Ruchu. Right, so first thing is clear, all these members are connected in series. And when the members are connected in series, the amount of load that will be acting in all the members will be same. So for the first member, the load acting is 100 kilonewton tensile. For second member also, the load acting is 100 kilonewton tensile. For third member, the load acting is also 100 kilonewton tensile. And the fourth member, the load acting is also 100 kilonewton tensile. So for all the members, the load acting is 100 kilonewton tensile. So load acting is 100 kilonewton tensile in all the members. In all the members, right? I'll just name these members. This is my member 1, this is member 2, this is member 3, this is member 4. In the above part, I have written areas, and in the lower part, I have written the Young's modulus for all the members, right? We also want length of the members. So this is like 0.5 meter, this is 1 meter, this is 1.5 meter, this is 1.5 meter, and this is again 1 meter, right? So these are the lengths of different members. So the first thing is, load acting in all the members is 100 kilonewton tensile. Now in order to calculate the total deformation, I need to calculate the individual deformation and then add up all these individual deformations to get the total amount of deformation. So the individual deformation delta 1 is equal to P L1 upon A1 into E1. P is 100 kilonewton tensile. So this is 100 into 10 raised to power 3. Length is given as 0.5. So this is 0.5 into 1000. So this is in mm. Sorry. Yeah, this is in mm. Divided by A1, which is 50 mm square. And E is 1 into 10 raised to power 5 megapascal, which is nothing but Newton per mm square. So when you calculate this deformation delta 1, this will come out in mm. This will come out in mm. Just quickly do the calculation and tell me the value. So this is 10 raised to power 5. This 2 will going to cancel out. You have 500 divided by 50. So this comes out to be 10 mm. So delta 1 comes out to be 10 mm. This is my delta 1, which is 10 mm, right? Similarly, do the calculations for other members also. Calculate delta 2, delta 3 and delta 4. So, delta 2 is P L2 upon A2 into E2. So, P is 100 kilonewton. So, 100 into 10 raised to power 3. L is 1 meter, so which is 1000 mm divided by A. So, A is, I guess, 100 mm square. So, this is 100 mm square. Multiplied by E, which is 2 into 10 raised to power 5. So, this 10 raised to power 5 and 10 raised to power 5 will going to cancel out. You have 1000 by 200. So, 1000 by 200 is nothing but 5 mm. So, your delta 2 comes out to be 5 mm. Moving on to the third deformation, delta 3. Delta 3 is again PL3 upon A3 into E3. So, P is same, P is 100 into 10 raised to power 3. So, this is in Newton. Length of this member is 1.5 meter. So, which corresponds to 1500 mm. So, this is 1500 mm length of the member divided by area. So, area is 20 mm square multiplied by the value of Young's modulus is 3 into 10 raised to power 5. So, value of Young's modulus is 3 into 10 raised to power 5, right. So, again here also you will get the deformation in mm. So, this 10 raised to power 5 and 10 raised to power 5 will going to cancel out. This is 3 ones are 3 5s are 500 by 20. 500 by 20. So, delta 3 is 500 by 20. So, this comes out to be 25 mm. So, this delta 3 comes out to be 25 mm. Now, moving on to the next, delta 4. Delta 4 is P L4 divided by A4 into E4. P is 100 kilonewton. So, 100 into 1000. Next, your L4 is 1 meter, that is 1000 mm, and your area is 120 mm square. So, this is your L4 1000 mm divided by area, which is 120 mm square multiplied by E. So, E is 0.5 into 10 raised to power 5 megapascal. So, these are the details given to us. Let me just check. Length is 1000. Length is 1000, area is 120 mm square, and E is 0.5 into 10 raised to power 5, right? So, these are the details given to us. Just calculate this delta 3 quickly. So, these two will cancel out with this. So, you have 1000 by 120 into 0.5. So, this comes out to be 16.67. So, your delta 4, 16.67 mm. This is your delta 4. So, in order to get the total deformation, we have to just add delta 1, delta 2 and delta 3, delta 4. So, total deformation is total deformation delta is equals to delta 1 plus delta 2 plus delta 3 plus delta 4. So delta 1 is, I guess, 10 mm, delta 1 is 10 mm, delta 2 is 5 mm, delta 1 is 10 mm, delta 2 is 5 mm, delta 3 is 25 mm, and delta 4 is 16.67 mm. So this is your total deformation in mm. 525, 16.67. So just calculate this. So this is 15 plus 25, 40, 40, 56.67. So this total deformation delta comes out to be 56.67 mm. So this is your total deformation for the members. So these type of questions for the bars connected in series like this you have to solve, right? You have to first assume, if you have to first analyze that all the bars will have the same amount of load. Second thing is, all the bars, in order to calculate the deformation, we need to calculate the individual deformation for all the members, and then we have to add the individual deformation to get the total deformation for all the members, right? So the total deformation is delta 1, delta 2, delta 3 plus delta 4. So this is for the bars connected in series. Next is bars connected in parallel. So let me again draw an example. So this kind of connection you have. So this kind of assembly you have where both the bars are connected to each other and they are connected in parallel, right? So this is the kind of assembly you have. This is my material 1 and this is my material 2. And both these bars are connected by the another support. Area is A1, length is L, and your Young's modulus is E1, right? Area is A1, length is L. I'll write this. Length of the member is L. For both the members, length is L. Area is A1 and Young's modulus is E1. Similarly, area is A2 and Young's modulus is E2. Length for both the members is same because they are connected in parallel. Now, how to analyze these type of members? For this member, the total amount of load that is acting is P. The total amount of load that is acting will be P, right? So just imagine you have these clamps. These two are clamps, right? In these clamps, these members are attached. And what you are doing, you are just holding these clamps and you are pulling with some amount P, right? What you did? You just hold this clamp and you pulled it by some amount P. When you pulled it by some amount P, the first thing that you will notice is these two clamps, these two side walls or clamps will going to deform by the same amount. This is the new position of the clamps. This is the new position of the clamps, right? These two clamps will deform by the same amount. They will deform by the same amount. So what it means that if the members are connected in series, both these members will undergo same deformation. Both these members will undergo same deformation. So whenever bars are connected in series, members undergo same deformation. Members undergo same deformation. And how we said that? For example, we have just hold this clamp and where these two members are connected and we just pulled it by some same amount of load P. So these two are the new positions of the clamp and we can clearly say this is the total deformation that happened to these clamps, right? So if this is the total deformation happened, it means that both the members are undergoing same deformation when they are connected in parallel. So whenever members are connected in parallel, the deformation will be same. That is your delta 1 is equal to delta 2 is equals to delta. Their same deformation will be there. They will undergo same deformation, right? Now one thing is very much clear. If they are undergoing same deformation and if these two members are made up of different material, that is they are having different Young's modulus, different areas, then obviously their load value will also be different such that their ratio becomes equal. This deformation of these two bars is nothing but the ratio of their load and area and Young's modulus, right? So that is how the load is distributed. So first thing is, when these two members are undergoing same deformation, the amount of load coming for member 1, say P1, for member 1, the amount of load coming is P1. For member 1, the amount of load coming over them is P1. And for member 2, the amount of load coming is P2. The amount of load coming over this member is P2, right? So the thing is, deformation for both the members will be same, but loads will be distributed. Loads in the member will be distributed. So the load in member 1 is P1, load in member 2 is P2. So this P1 plus P2 will equal to P. So this is how your load will be distributed. This entire load P will be distributed in P1 and P2 depending on the nature of Young's modulus and the area of cross section of the members. Because length of the members are same, that's why this distribution depends on the area of cross section and the Young's modulus of the two different materials, right? Now the next topic of discussion is how to get how much amount of load these two members will be having. That is the calculation of P1 and P2, okay? So again we will proceed with the same thing. We have one relation which says that your total deformation is equal to the individual deformation of the members. So we will write the individual deformation of the member. So for member 1, your delta 1 is equal to P1 L upon A1 into E1. This is the deformation for the first member. Similarly, for second member, your delta 2 is equals to P2L upon A2 into E2, right? And we know this delta 1 is equal to delta 2. We know this delta 1 is equal to delta 2. So I will write P1L upon A1 E1 is equals to P2L divided by A2 into E2. And I think this is very much clear to you. Your total deformation is same. Therefore, we are able to write this. P1L upon A1 E1 is equals to P2L upon A2 into E2. So this is the deformation, right? Next, moving on with this equation. Next equation is, we know that P1 plus P2 is equals to P, right? So either substitute P1 in terms of P2 or P2 in terms of P1. That is totally up to you. I am substituting P2 in terms of P1. So I will write P1 and here I will write P1 into A2 E2 divided by A1 E1 is equals to P, right? When you take P1 common, you have 1 plus this term. And 1 plus this term will be A1 E1 plus A2 E2 divided by A1 E1, right? So what I did, I took P1 common. So I took P1 common. I took P1 common and then I have just taken the LCM. So A1 E1 plus A2 E2 divided by A1 E1 is equals to P, right? So from here I can get the value of P1. So P1 is equals to P into A1 E1 divided by A1 E1 plus A2 E2. And this is how we calculate the value of P1. Now observe this P1, right? This P1 is nothing but the weighted average of this P with respect to your axial rigidity. Whatever is the axial rigidity for a member, weighted average of that axial rigidity will be your load P1. Similarly, if you calculate load P2, P2 will be like P into A2 E2 divided by A1 E1 plus A2 E2. This is your weighted average for your load P2. Right. So your individual load, I'll write this individual load is the weighted average of axial rigidity, is the weighted average of axial rigidity. Is the weighted average of axial rigidity, right? You may seem, sir, how to remember these formulas? I'm saying do not remember these formulas. Just observe the figure and make these formulas, right? And I'll tell you how you can do this. For suppose you are given with 3 members. You are given with 3 members like this. You are given with 3 members like this. This is first member, then this is your second member, then this is your third member, right? And for these three members, you have different values of cross-sectional area and you have different values of Young's modulus. So you have three members given to you. I even shade these three members so that you do not have any confusion. So this is my member 1. This is my member 2. And this is my third member. Right? So three members are given to us. Length of all the three members is L. Length of all the three members is L. Length of all the three members is L. For first member, area is A1 and Young's modulus is E1. For second member, area is A2, Young's modulus is E2. For third member, area is A3 and Young's modulus is E3. The total amount of load that is acting over this assembly is P. The total amount of load that is acting over this assembly is P. This is A2 and E2. This is L, right? The total amount of load that acting over this assembly is P. This is member 1, this is member 2, and this is member 3. Now you need to write individual loads that will be coming over these three members. So what you have to do is, you have to simply write P1, right? And equal to P, that is the total load. Then write axial rigidity of member 1. Axial rigidity of member 1 is A1 E1. It is A1 into E1. Axial rigidity of member 1 is A1 E1. This is the axial rigidity of the member. In the denominator, write axial rigidity for all the members. A1 E1 plus A2 E2 plus A3 E3. This is the axial rigidity for all the members. This is the load P1. As simple as that. So if n number of members are connected, what you have to write? You have to take the weighted average of this load. And the weighted average should be with respect to the axial rigidity A1 E1, right? Similarly, if you have to write P2, P2 is nothing but P, axial rigidity of the second member. Axial rigidity of the second member is A2 E2. And then in the denominator, write axial rigidity of all the members. That is A1 E1 plus A2 E2 plus A3 E3, as simple as this, right? Lastly, if you have to write P3, so P3 is again, for P3, load P into the axial rigidity of the third member, that is A3 E3 divided by the total axial rigidity, that is A1 E1 plus A2 E2 plus A3 E3. And through this simple trick, you can write all the loads of the individual member without even solving the question, right? Without even doing the complicated calculation or equation solving, you can directly write the load for different members if the bars are connected in parallel, right? So if the bars are connected in parallel, the first thing is the total deformation of all the individual members will be same. So I'll write here individual deformation will be same. So your individual deformation delta 1 will be equal to delta 2 equal to delta 3 is equals to total delta, right? So your individual deformation will be same. but your individual loads will be different for the 3 members. And this is how you calculate the individual load for the members if they are connected in parallel, right? So just try this question. Just try this question quickly. This is my first member, and then I have the second member. I'll take one more member, 3 member. So these 3 are the members. For these 3 members, they are connected by a clamp like this. They are connected by clamps, right? Area for first member is 50 mm square, and Young's modulus is 2 into 10 raised power 5 megapascal. This is E1 and this is A1. Similarly, for this second member, okay, I'll write here, it will create confusion, right? So this is my member 1, this is member 2, and this is member 3. All these 3 members are connected in parallel. The total load acting is 500 kilonewton. Total load acting is 500 kilonewton. Length of all the members is 1 meter. Length of all members is 1 meter. For first member, A1 is 50 mm square and E1 is 2 into 10 raised power 5 megapascal. For A2, area is 100 mm square and E2 is 1 into 10 raised power 5 megapascal. For A3, area is 120 mm square and E3 is 3 into 10 raised power 5 megapascal. Right? From here, I would like you to observe 2 things. First is how much load every member is getting. Second thing is you also need to understand if the value of Young's modulus is more, then what is the effect of the load bearing? That is, if the Young's modulus is more, then the amount of load handled by a particular member will be more or less. That also you have to analyze, right? So for this question, first thing that you need to calculate is calculate deformation for all the members. Deformation for all members. Second is loads in all the members. Loads in all the members. Deformation in all the members and loads in all the members. So these are the 2 things that you need to calculate for this question, right? So again, this is a simple question for members connected in parallel and you need to solve this, okay? Whenever members are connected in parallel, the first thing is clear that deformation of all the members will be same, right? And that can be calculated either by calculating the deformation for member 1, member 2 or member 3, right? So the total deformation is same. So if deformations are delta 1, deformations are delta 1, delta 2 and delta 3, then your delta 1 is equal to delta 2 is equals to delta 3, right? So using any of the deformation, you can calculate the total deformation for the members. So delta 1 can be calculated as P1L upon A1 E1. Delta 2 can be calculated as P2L upon A2 into E2, and delta 3 can be calculated as P3L upon A3 into E3, right? Total load is 500 kilonewton, but the individual loads of the members will be different. Now the thing is, we need to calculate this individual load. So either you make the equation, solve the equation and get confused, or directly use the short trick that we have just seen, right? So we were going to see this trick. So if I have to write P1, so how can I write P1? P1 is equals to P into axial rigidity of first member, that is A1 E1, divided by the total axial rigidity for all the members, that is A1 E1 plus A2 E2 plus A3 E3. As simple as that. P1 is equals to load P multiplied by axial rigidity of first member divided by the sum of axial rigidity of all the individual members. So P1 is 5000 kilonewton. So 500 kilonewton. So I'll write this 500. A1 is 50 mm square and E1 is 2 into 10 raised to power 5. So this is 50 into 2 into 10 raised to power 5, right? This is A1 E1. So I'll write 50 into 2 into 10 raised to power 5. Second, A2 is 100 mm square and E2 is 1 into 10 raised to power 5. So this is 100 into 1 into 10 raised to power 5. This is A2 E2. Then A3 E3 is 120 into 3 into 10 raised to power 5. So this is 120 into 3 into 10 raised to power 5. This is your A1 E1 plus A2 E2 plus A3 E3, right? So first of all, let me calculate this denominator. This denominator is 100 plus 100, 200, 200 plus 360. 200 plus 360 is 560. So 560 into 10 raised to power 5. So this P1 is equals to P, that is 500 into, this is 50 into 200 into 10 raised to power 5 divided by 560 into 10 raised to power 5, right? So I have just calculated the denominator. So this 10 raised to power 5 and 10 raised to power 5 will going to cancel out. It will be 100 by 560 into 500. So how much it is? So 100 divided by 560 into 500. So this comes out to be 89.28 kilonewton. So P1 comes out to be 89.28 kilonewton. So this is my first P1. Similarly, I can calculate P2 and P3. P2 and P3 will be like, I'll just write this down. So P2 will be like, P2 is equals to P into A2 E2 divided by A1 E1 plus A2 E2 plus A3 E3. So this is how you calculate P2. Substitute the value of A2 E2. So P2 is equals to P, which is 500 kilonewton. So this is 500 multiplied by A2 E2. A2 E2 is nothing but 100 into 1 into 10 raised to power 5. So A2 is 100 and E2 is 1 into 10 raised to power 5. This entire denominator A1 E1 plus A2 E2 plus A3 E3 we have already calculated. It is 560 into 10 raised to power 5. So this is 560 into 10 raised to power 5. So again this comes out to be 100 by 560. So 100 by 560 is again 89.28 kilonewton. So P2 comes out to be 89.28 kilonewton. kilonewton, right? Now moving to P3. So P3 is equals to P into A3 E3 divided by A1 E1 plus A2 E2 plus A3 E3. Right, so if you just substitute everything, so you have P3 is equals to P, which is 500 kilonewton. So 500 into A3 E3 is 120 into 3 into 10 raised to power 5. So area is 120 and Young's modulus is 3 into 10 raised to power 5 megapascal. This denominator we have already calculated, which is nothing but 560 into 10 raised to power 5. Right, so just do the calculation and get the value of P3. So P3 is 500 into 120 into 3 divided by 560. So this comes out to be 321.43. 321.43 kilonewton. kilonewton. So we have all the values of P1, P2 and P3, right? Now observe this very carefully. Axial rigidity for member A, for member 1, axial rigidity for member 1 is 50 into 2 into 10 raised to power 5. So this comes out to be 100 into 10 raised to power 5. So for member 1, A1 E1 is, A1 E1 axial rigidity is 100 into 10 raised to power 5. For member 2, axial rigidity is also, axial rigidity A2 E2 is also 100 into 10 raised to power 5. Since axial rigidity for both these members are same, therefore the amount of load coming in member 1 and member 2 is also same. So you can look clearly, this is member 1, the amount of load is 89.28 and the member 2, the amount of load is 89.28. So for the members having same amount of axial rigidity has the same amount of load coming over them. This member 3 has more axial rigidity, which is 120 into 3, that is 360 into 10 raised to power 5. Since the axial rigidity for the third member is more, hence the amount of load coming over this member will also be more, right? So this P3 is more. Now you need to calculate deformation delta. So deformation delta, I'll calculate through delta 1. Delta 1 is P1L upon A1 into E1. P1 is 89.28 and it is in kilonewton. So I'll write 10 raised to power 3 converting into Newton. Length of the member is given as 1 meter. So length of all the members is given as 1 meter. So length of all the members is given as 1 meter. So this is 1000 mm divided by A1. A1 is 50 mm square and E1 is 2 into 10 raised to power 5. So this mm will going to get cancelled and you have mm as the final answer. Newton and Newton cancels out. This mm square and the mm square in the denominator of megapascal will cancel out and you have the final answer in mm. So get the deformation delta 1. So this is 89.28. So this is 10 raised to power 3 and 10 raised to power 3. This is 10 raised to power 6. This is also 10 raised to power 6. 5 plus 1, 6. So these two cancels out. So you have 89.28 divided by 10. So this comes out to be 8.928 mm. So delta 1 comes out to be 8.928 mm. This is your net deformation for first member. Right. Similarly, you can write delta 1 is equals to delta 2 is equals to delta 3 is equals to 8.928 mm. So this is your net deformation for all the three members. So this is how you can deal with the members if they are connected in parallel or if they are connected in series. So this is again an easiest method. If I just summarize these two things, you should be very clear. If the members are connected in series, then the amount of load acting over all the members will be same. The total deformation is the sum of individual deformation, and this is for members connected in series. For members connected in parallel, the total deformation of all the members will be same. For members connected in parallel, the total deformation for all the members will be same, and the amount of load coming all over individual members will be the weighted average of the total load with respect to their axial rigidity, right? So this is how you need to deal with all these questions of parallel and series. Now moving on to our next topic. Next topic is deformation under self weight. Deformation under self weight. So whichever case we have considered, we have not considered the weight of the member. In fact, in the entire discussion of strength of material, we just ignore the self weight of the member. But here we have one specific discussion regarding how the member will deform under its self weight. So for suppose you have this member hanging from the roof. You have this member which is hanging from the roof. You have this member which is hanging from the roof, right? This is the member which is hanging from the roof. This is the member which is hanging from the roof. I'll just give you the detail what all things are given to us. We know the area of the member. So given data is, we know area of the member is A. It is a prismatic section, means the cross-sectional area is constant throughout the length of the member. So it is a prismatic section or a prismatic member, not section, prismatic member. Length of the member is L. Length of the member is L. The entire length is L. The length of the member is L. Next, the unit weight of the member is gamma. Unit weight of the member is gamma. Next, Young's modulus is E. Young's modulus is E. Young's modulus is E, right? And we need to calculate the total deformation this member will undergo under its self weight, correct? Before this, whenever we are calculating the elongation for the member, two things are common. First is the member was prismatic. So here also the member is prismatic. Length of the member is L and area is constant. So these two things are common. Now, in the previous case, when we were calculating the total elongation for a particular member, for that particular member in the entire length, the load acting was also constant, right? So if you consider any previous example, you will find that if we are calculating the elongation for a particular member, from starting point till the end point of the member, the load acting is same. But for this member, if you go at any height, say this is the height. If you go at any height, say this is some height x. If you go at any height, the amount of load acting will the weight of this member. The amount of load acting will the weight of this member which is hanging below it. If you go somewhere more higher, the amount of load which is acting over this member will going to increase. If you go somewhat more higher, then the amount of load that will be acting over this member will be this, right? This total length, the weight of this hanging member. So we need to find the total elongation of this member under its self weight. Understood the situation? Situation is, whenever you go by a certain height in the member or above the member, the amount of weight that is hanging below the section will going to increase. So as you keep on moving, the amount of weight that is hanging below it will going to increase. So in the entire length, the load is not constant. And when the load is not constant and we need to calculate the deformation, the only technique that we have is to integrate the total deformation. Now observe this very carefully how I am calculating this, right? Let me take one section at some distance x from the bottom fiber, right? Just tell me what is the weight at the bottom fiber? What is the amount of weight hanging below the bottom fiber? The amount of weight which is hanging below the bottom fiber is 0. No weight is hanging below the bottom fiber, right? But when you take one fiber at some distance x, when you move by some amount of distance x, and you consider this section, which is having, the length of dx. What I am saying, you consider this section having the length of dx. Consider this section at some distance x. For this length dx, I am going to calculate the deformation due to this load which is hanging below it. What I did, I just moved up by some amount x, and at some distance x from the bottom fiber, I have considered this length dx. And over this length dx, I am going to calculate the amount of deformation, that is the change in length due to this hanging load x. So consider length dx. Calculate deformation. Over length dx. So the deformation that will be coming over length dx will be d delta. D delta is the deformation coming over length dx due to the weight hanging below it, right? So the deformation that is coming over length dx is equal to the weight of the member that is hanging below it. right? So for this length dx, this is the load which is acting and causing the deformation. So the weight of this length, the weight of this length will be the load acting over this length dx. So how can you write weight of this length? Weight of this length is nothing but weight of this length. So weight of this length is nothing but area multiplied by length, that is A into x, will going to give us the volume of this length. And volume multiplied by the unit weight is the weight of this length that is hanging below this length dx. So the total amount of weight acting over this length dx is A into x into unit weight of this material, right? So the weight acting is weight acting is A into x multiplied by the unit weight. Length of the member is dx. Length of the member is dx divided by A into E. PL by AE, and that is how you calculate the d deformation over length dx. What we calculated? We calculated the deformation over length dx. Length is dx, right? So this A and A cancels out, and you have d delta is equals to gamma by E into x dx, right? In order to calculate the total deformation, just integrate this expression. So on integrating this expression, and integration will be from 0 to L. The total integration will be from 0 to L. So integration will be from 0 to L. 0 to L. Just 1 minute. So integration of d delta is equals to integration of, I'll take gamma by E outside because these two are constants, integration of x dx from 0 to L. So the total deformation delta comes out to be gamma L square divided by 2E. So this is the total amount of deformation that will going to come under the self weight of the member. This is the total deformation that will come over the member under its self weight, which is equal to gamma L square by 2E. So if any statement comes in the examination that whether the deformation due to the self weight depends on the cross sectional area, you will say no. The deformation under the self weight will only depend on the length of the member, the unit weight of the material, the Young's modulus of the material. It will not going to depend on the cross sectional area of the material. So you will find most of the question in examination where the self weight has to be deformation under the self weight has to be calculated when and different conditions of areas are given. So I'll just note these points down. So deformation under self weight, deformation under self weight will depend on length, unit weight, and Young's modulus. Deformation under self weight deformation under self weight will not depend on, will not, not, will not depend on cross-sectional area of the member, will not depend on cross-sectional area of the member. Cross-sectional area of the member, right? These two statements are important because in the examination, either you can get a calculation of calculating the total deformation under the self-weight, or you get a question like in comparison form, right? Just try this question quickly. You have one question for the examination which says, if area is doubled, if area is doubled, if area is doubled, what change will happen to the deformation under self-weight? Under self-weight. What change will happen to the deformation under self-weight? Four options are given to you. Doubled becomes 4 times, becomes 4 times, becomes half, becomes half, and option D is no change. Just quickly get me the answer for this. If you have a member and for that member, if area of cross section is doubled, what will happen to the deformation under its self weight? So, if you have a member like this, for which the cross sectional area is A, length is L, cross sectional area is A, length is L, Young's modulus is E, unit weight is gamma, right? For this member, which is having A, E, gamma and L. L is the length of the member. For this member, the deformation under the self weight, so delta is gamma L square divided by 2E. Right? For this member, the deformation under the self weight is gamma L square divided by 2E. Even if the cross section is doubled, you can clearly observe that there will be no change in the deformation of this bar under the self weight. So, the deformation of the bar under the self weight will not depend on the cross sectional area of the member. It will only depend on the length, unit weight and the Young's modulus of the member. So, for this question there will be no change. So, option number D is correct. Option number D is correct. Option number D is correct. Right. Similarly, there are other varieties of question where the relation between length and unit weight will be given. If a question says if the length is doubled, what will be the change in deformation under self weight? So, you will say, sir, if the length is doubled, the deformation will become 4 times. What change will happen if the length is halved? So, if the length is halved, means the length is now L by 2, your deformation will be reduced by 4 times. So, this relation you should remember, and for this relation you should remember the dependency of this deformation over the length, unit weight and the Young's modulus. The deformation under self weight does not depend on the cross sectional area. So, it does not matter if your cross sectional area is same or different, your deformation will remain same. But if there is any change in the length of the member, unit weight of the member and Young's modulus of the member, then surely your deformation will going to change, right? So n number of questions are there in your GATE examination, and through this fundamental concepts, you can very easily handle those simple questions, right? So hopefully for today's session, you learned a lot about how to calculate elongation for the bars when the bars are connected in series and parallel, and also how to calculate elongation of the bar under its self weight. So this is all for today. Thank you so much for watching patiently, and continue with our series so that you can have the concepts of the remaining topic. So I'll see you tomorrow, same time, same place at the YouTube channel of IMS GATE Academy. Thank you so much.